Welcome back. In this session we will solve in this problem that is on beams. Okay, see here, this is a beam where some portion there is no load, and in this portion it is subjected to UDL. So let us consider the portion where there is no load as the element 1, and with the portion where the UDL is acting, that is element 2. So the number of nodes are 1, 2 and 3. We already know that each node has 2 degrees of freedom. So V1 theta 1, V2 theta 2 and V3 theta 3. We need to find stiffness matrix to find the nodal displacements. So now we have two elements. For the element 1 there is no load. So V1 theta 1, V2 theta 2. Okay, let us find the stiffness matrix for the element 1. We already know how to find the stiffness matrix of the element 1. Young's modulus it is given. You convert it to kilonewton per meter square. You convert I as a meter raised to 4. Okay, substituting EI LU cube by, and length of the element, length is 1 meters. Okay, you get this matrix. Similarly, you find the stiffness matrix for the element 2. Again it requires EI LE cube. EI is same, length is also same, so you will get the same matrix. Now the degrees of freedom are not same for the two elements. It is V1 theta 1, V2 theta 2 for the element 1, and for the element 2 it is V2 theta 2, V3 theta 3. So you add two matrix, stiffness matrix 1 and stiffness matrix 2. This process is called as the assembly of the stiffness matrix. Okay, so the size of the stiffness matrix is 6 by 6. Why it is 6 by 6? In each node there are 2 degrees of freedom, and we have 3 nodes. 3 into 2, 6. V1 theta 1, V2 theta 2, V3 theta 3. V1 theta 1, V2 theta 2, V3 theta 3. The first 4 by 4 matrix, this is of element 1. Then this one, it is of element 2, and 24008 there the stiffness matrix values are overlapped from the element 1 and element 2. It is added there. You already know how to take in this fashions. You already solved finding the global stiffness matrix in the bars problem and trusses problem. Now KQ is equal to F. Okay, KQ is equal to F, where K is the global stiffness matrix, Q is the nodal displacement factor. What are the nodal displacement? V1 theta 1, V2 theta 2, V3 theta 3. Node 1, what is the constraint there? Okay, node 1 it is fixed, so V1 theta 1 is 0, and node 2 there is no vertical displacement, it is a roller support, so V2 is 0 and V3 is also 0 as it is a roller support. So the unknowns are theta 2 and theta 3. Now what are the loads? Now you need to find the force vector for the element 1 and element 2. For the element 1, there is no force acting on the element 1, so F1 M1, F2 M2 all are 0. F1, that is the force in the node 1, and M1 is the force in the node 1. Similarly F2 M2 are the force and moment in the node 2, all are 0. And in the element 2 it is subjected to UDL. Element 2 it is subjected to UDL. How to find forces for UDL? You already know, P naught L by 2, where P is the what is the intensity of loading, L is the length of the element. Okay, by this you find what are the force and moment at node 2 and node 3. Okay, this is the force vector 2. Okay, then this is the global force vector. Okay, substitute, you place all this in this form, KQ is equal to F. By elimination approach method we know that node 1 is fixed. Node 1 is fixed means V1 is 0, theta 1 is 0, so first row first column, second row second column can be deleted, and there is a roller support at node 2. Roller support means V2, there is no vertical displacement. Third row third column can be deleted. Similarly, there is lower support at node 3, so there is no vertical displacement, so it is the fifth row and fifth column deleted. So it is reduced to 2 by 2 matrix. Simplifying this, you will get theta 2 and theta 3 values. So other nodal displacements are 0. Okay, if you want to find the deflections, you use V is equal to HQ for the element 1 and element 2. You already know how to find the deflection. H1 V1, LE by 2, H2 theta 2, S3 V2, LE by 2, V1 it is theta 1, you make it theta 1, and V2 it is theta 2, you make it, sorry, it is for the element 2, so it is right. This is V2, this is V2 and theta 2, this is V3 theta 3. You make this correction for the element 2 to find the deflections. V2 theta 2, V3 theta 3. Okay, find the deflections by substituting the values. Okay, similarly in this problem, it is subjected to loading for the whole length, but for the first half the intensity is 12 kilonewton per meter, so it is 24. So you take the 12 kilonewton per meter intensity as the element 1, and this 24 kilonewton per, this is element 2. Okay, you find the stiffness matrix for this element and stiffness matrix of this element as the element 2. It is K1 K2. Okay, find K1 and K2, assemble the two stiffness matrix. What are these nodal displacement here? It is V1 theta 1, V2 theta 2, V3 theta 3. Okay, find the stiffness matrix. EI is given, convert it to kilonewton per meter square, this Young's modulus, and it is meter raised to 4. Okay, K1 and K2 are given, you already know how to. Then add this K1 K2, so it is the global stiffness matrix. Then you find the force vector. Okay, for both vectors you use the same equation because both are UDL. For the first element, this P0 is 12, so substituting P0 as 12 and the length of the element is 4 meters, you will get F1 M1 F2 M2. Similarly, you find one more force vector for the element 2. There you substitute this P0 as 24 and the length of the element is 4. Okay, substituting all this value, you will get a force vector 1 and force vector 2. Then you find the global force vector. Okay, this is F1 M1 F2 M2. See here, F2 M2, you will get F2 and M2 value in the both elements. So the terms which occupy this position will be added. So see here, this in the first force vector for the element 1, V2 theta 2 is there. Here also V2 theta 2 is there. In the global stiffness matrix, what you have to write? V1 theta 1, V2 theta 2 and V3 theta 3. So V2 from the element 1 and V2 from the element 2, it should be get added. Minus 24 plus minus 42, that is minus 72. Same theta 2, both terms are there in the element 1 and element 2. That plus 16 minus 32, that is 16 minus 16. Okay, then you take in this form. What are the constants here? Okay, V1 theta 1 is 0, V2 is 0, V3 is 0. So you will again get a 2 by 2 matrix. The corresponding rows and columns can be deleted. So the unknowns are theta 2, theta 3. And to find the deflection, you use this equation. Okay, V is equal to HQ, where H is the Hermite function. H1, H2, H3, H4 values are derived. Q, it is the nodal displacement vector. What you are finding here? To find the maximum deflection at the midpoint. Okay, for the element 1, you use H1, H2, H3, H4. For element 2 also you have to use the same, but nodal displacements, it is not same for the both. Here you are using for the element 1, it is V1 theta 1, V2 theta 2. For the element 2, V2 theta 2, V3 theta 3. Okay, solve this, you will get the deflections, maximum deflections at the center point. Okay, thank you.